Hi friends, this is Mr. Zarzak, and in this video I'll be taking you through how we analyze projectile motion for more complex problem solving. I'm going to follow the approach that we lay out for you using this projectile problem template. Okay, I'll refer back to it several times throughout the video. I'm just going to kind of work the problems, but as you watch the video, you'll see that I'm following the steps that are laid out in this template to kind of guide how I'm going to attack these. Okay, so the first thing we need is some initial information about our projectile. So we're going to say that our projectile has an initial speed of 28 meters per second, and we're going to launch it with a direction of, let's say, 53 degrees above the horizontal. Okay, so when we deal with this, the first thing we're going to do is we're going to take this angled projectile. Okay, so we say that 53 degrees above the horizontal. We're going to break it up into components. All right, so in order to do that, I'm going to find this horizontal component. I'm going to take my 28 meters per second, multiply it by cosine of 53 degrees. And from my Vy, I'm going to take the 28 meters per second and multiply it by the sine of 53 degrees. Okay, if I put those into a calculator, I'm going to find that my Vx is 16.851 meters per second, and my Vy is 22.362 meters per second. Okay, so if I just scroll down a little bit here, there's some places that I can put this in. That Vx over here in the x column, so any kind of horizontal or sideways motion, 16.851 meters per second. Okay, notice that there's just one Vx because sideways there's no accelerated motion in the classic projectile problem. Vertically, that's a different story. This 22.362 meters per second, that's the initial velocity in the vertical dimension. The reason being is that we do have accelerated motion up and down because, well, projectiles are things with initial velocities that are then controlled only, or their motions are dictated only by that of their initial velocity and gravity. Okay, so I'm going to use 9.8 or negative 9.8 meters per second squared for this. You can use negative 10 as well. It really doesn't matter. Okay, so anyways, so what are we trying to solve for this? Well, I want to do a little bit more complicated analysis than just shooting the thing in the air and letting it come back down to the ground. So let's say that we wanted to launch our projectile and have it land on some ledge that was 13 meters above the ground. Okay, so this is kind of like the initial. So we shoot it like this. There's our V. Okay, that's our angle. Okay, that was our initial information. Notice that I've just transposed the components down here, because actually once I have these two components, any of that diagonal information, I don't need it anymore. Okay, for the rest of the problem, I'm just going to use the vertical and the horizontal component independently. All right, and then if I'm going to launch it up to a ledge, it's like saying, well, it's going to land at some distance that's 13 meters above where it's launched. Okay, and I don't have to put the little positive sign, but it's going to help me figure out what I need to do next. All right. So anyways, if I scroll back to this, and the x column says, do I know two of the values? If so, I can solve for the third. But, well, I only know that horizontal component, the velocity. So if I shift over to my right-hand column, it says if you wanted to use the time, okay, we're going to use this displacement equation. All right, and that's exactly what we're going to do down here. All right, so let's just go through the steps. Okay, I'm going to look up and down, so I'm only in my y dimension. The vertical displacement is equal to my initial velocity in that vertical dimension times the time plus 1/2 acceleration times time squared. Okay, so if I'm going to launch up to this ledge that's 13 meters tall, that initial vertical velocity that's 22.362 meters per second, okay, times my time plus 1/2 negative 9.8 meters per second squared for gravity. Again, if you want to use 10, negative 10, that's fine too. Okay, what I'm looking at here is I have one equation, I have one unknown. So the only thing I don't know here is the time, which means that I can solve it. Okay, so that's exactly what I'm going to do. I'm going to clean this up just a little bit. So 13 is equal to 22.362 times t, just to make it a little easier to see what I need to do, minus 4.9 t squared. Okay, I'm going to do a little bit of rearranging here. Okay, I'm going to move the 13 over, so keep the negative 4.9 t squared, keep the 22.362 t. I'm just going to bring that 13 over on this side. Okay, and when I do that, I see that I've got a quadratic. Okay, with a negative 4.9, that's my A. The 22.362, that's my B. And the negative 13, that's my C. Okay, so in order to solve for the quadratic, the time is going to be equal to negative B plus or minus the square root of B squared minus 4AC, that whole quantity over 2 times A. So if I sub in my numbers, okay, the opposite of B would be minus 22.362 plus or minus the square root of 22.362 squared minus 4 times A, which is my negative 4.9, times my C, which is negative 13. All of that over 2 times negative 4.9. Okay, so if I plug that all into my calculator, I'm going to get 2 different times. And I'm actually going to find that I get 2 times that are both positive values. So I get 0.684 seconds, and I get 3.880 seconds. Okay, so these are both positive, so which one is the correct time? Okay, if I go back up to my sketch, all right, well, this 13 meters, this actually happens twice. Okay, the projectile reaches this height once on the way up and then once on the way down. So this one over here that I've got, this would be that first time, that point, what did I say, it was 0.684 seconds. All right, and that's not the one they're interested in, because if we launch it like this, we're going to run into the ledge. We're not going to actually land on the ledge. And that's what we want to do, is we're kicking the thing or throwing the thing or launching the thing up to some ledge. Okay, so that's not the one that we want. We actually want this secondary dy, okay, when the thing is on its way back down. Okay, so for our purposes, this is the time that we're interested in. Okay, now once I have that time, there's a whole bunch of things that I can figure out. Okay, so just kind of, I could scan back to the template. I don't want to scroll too much because I don't make anybody dizzy here. All right, but I'm going to find the range of the projectile. So how far sideways has it moved at this point? To do that, okay, I just take the horizontal velocity and multiply it by the time. All right, now technically speaking, what this is VIT plus 1/2 AT squared, okay, but there is no sideways or horizontal acceleration with the projectile. Only gravity's in there. So if my A is 0, all right, well, this whole term just shrinks to 0. I'm just left with the horizontal speed times that time is the horizontal distance. Okay, so if I sub that in, all right, that horizontal component, to go back up to the top here, 16.851. 16.851 meters per second. All right, times this time of 3.880 seconds. Okay, put those two together in my calculator, and you should get 65.382 meters. Okay, so that's the sideways distance that the projectile travels, or what we call the range. Okay, and then we could calculate all kinds of things. Here, let's just keep going with this. Let's say we wanted to figure out its final vertical velocity. That's one of the things that's on our little template, is we could figure out in this y direction, we could find the final velocity in the y direction. Okay, we take the initial velocity in the y direction plus acceleration in the y direction times time. All right. So remember, in that vertical dimension, things change because of gravity. Initially, my velocity up and down was that 22.362 meters per second. So 22.362 meters per second. There's my initial vertical velocity. Okay, my acceleration up and down, well, down I should say, is just gravity. All right, times this time that we calculated up before. This was at 3.880 seconds. Okay, so then if I throw that in the calculator, I'm going to get a value of negative 15.662 meters per second. All right, now in terms of the template, that's pretty much all the things that I can calculate. If I wanted to take it even further, and why not, we've come this far. Okay, well, notice the negative sign. We defined up as the positive direction when we set gravity is equal to negative 9.8. So what this tells us is at this point, all right, the projectile's motion, okay, is downward. So there's like a downward component to the Vy. Okay, well, that x component, which was that 16.851 meters per second. Okay, well, that maintains that sideways motion. It does not change. So it's moving sideways at this 16.851 meters per second the entire time it's in the air. Okay, so if I have a downward component and I have a rightward component, there's my Vx. Okay, so the components point to the right and down. So the resultant points down to the right just like that. So if I wanted to solve for that, I could use Pythagorean theorem. I get Vx squared plus Vy squared square rooted. Okay, and so I just take it, I'm going to plug in that, where is it, 16.851. That's the Vx that we started with. Square that. Add that to negative 15.662 meters per second. That's my Vy squared. Okay, and if I throw that into a calculator, I should find 23, looks like 0.006 meters per second. So that would be the value of that right there. That's how fast it's moving. Notice that that doesn't get a sign because it's not along either my x or my y direction. So there's no positive and negative diagonals. It's just speed and then direction. So there's 23.006. It's only half of the final velocity answer. We need a number for the direction too. So to get that, okay, technically I've got all three pieces of the triangle. I like to use inverse tan. Okay, now notice on my picture, okay, I'm defining the angle. That angle is an angle somewhere between 0 and 90 degrees. It's below the axis, but I'm really just looking for the magnitude of the angle. So I'm just going to plug in the magnitude of my two components. I'm really just interested in the size of that angle. So I plug in my Vy and my Vx. Okay, and if I put that in the calculator, I should get a value of 42.906 degrees. Okay, and I can see it on my picture. If I wanted to put it with words, that would be like below positive x-axis. Okay, but like I said, as long as I have the picture, I'm all right. Okay, so those are kind of what we can calculate from that initial information. I wanted to take and, before we stop, okay, I actually wanted to rework this problem again. Okay, but I wanted to rework this problem where we made one minor but really important change. Okay, so I have a second copy of the template with the same initial information. So 28 meters per second, 53 degrees above the horizontal. Okay, so same components. All right, so I filled those in here. All right, same acceleration of gravity. Okay, but now what I'm going to change, okay, is I'm going to launch into a canyon that's 13 meters deep. So instead of up to some ledge that's 13 meters above, I'm going to launch down. Okay, so again, I still got the same, right? So there would be my initial V, and there would be my angle. Okay, I take the thing and I break it up into components. And again, once it's into components, any of that diagonal information, I'm not going to use it anymore. Just Vy and Vx, okay? But the hitch now, okay, is that the projectile is now going to land some distance below where we launch it. So now my dy, we said this would be like negative 13 meters below where we launch. Okay, so same basic approach. I've got my components. All right, I only know the horizontal component of the velocity. I don't know the dx, so I can't get the t, or I don't know the t, so I can't get the dx. So I'm going to have to solve for that time. Okay, so nearly identical approach in that I'm going to use the same equation. Okay, so it's displacement equation. Vi t plus 1/2 at squared. Okay, and again, once it's in the air, the only acceleration is gravity, so I'm working in that vertical dimension. Okay, but now I'm going to land 13 meters below. Okay, that little negative sign, it's important, changes everything. Only changes everything when I calculate anyway. All right, so that 362 meters per second. There's my initial vertical velocity times the time, plus 1/2, negative 9.8 meters per second squared for gravity. Again, if you want to use negative 10, that's totally fine too. Okay, in most cases I use negative 10. I don't even know why I chose to use negative 9.8 on this. I just did. 22.362 times t minus 4.9 t squared. Okay, and you can see that it's, again, it's going to be a quadratic. so let me just get this set up here. So negative 4.9 t squared plus 22.362 t plus 13. Okay, and if I identify, so there's my A, there's my B, and here's my C, a positive 13. So now, when I go and I set up my quadratic, so negative B plus or minus square root of the quantity, B squared minus 4AC, all over 2A. Okay, so now when I plug in, let's see, negative 22.362 plus or minus 22.362 squared minus 4 negative 4.9 times positive 13. So it's going to change what's underneath that radical. Okay, which means that we're going to wind up with two different values for our time. Okay, so when I evaluate the quadratic now, let's see, I'm going to get 2 times. I'm going to get it. One is negative 0.522 seconds, and the other one is a positive 5.085 seconds. Okay, we know that, well, time is a scalar. Time can't be negative, so that one's got to go away. Okay, it says 5.085 seconds. We only wind up 13 meters below one time. It doesn't hit it a second, a first time and a second time. No, it only winds up 13 meters below once. Okay, so it's neat that the equation shows us that. Once we have, that time, well, then we can go on and calculate all the things that we did before. All right, so we get the horizontal distance. We get the Vx times the t. Okay, so the same 16.851 meters per second that we've been working with. All right, but now this time of 5.085 seconds. So I get this range. So different range now. So 85.687 meters. Okay, so it goes farther now before it gets to it, because it's going to not only return to its original height, it's going to fall down an additional 13 meters. Okay, if I wanted to, I can compute the final velocity up and down. I guess I should add some labels. Okay, so initial y plus acceleration times time. And again, I'm just following along with what's on the template. So if you've got that handy, take a look and you can really see that I'm just following the exact steps. All right, the initial vertical was the 22.362. 22.362. Okay, plus negative 9.8 meters per second squared times this time of 5.085 seconds. Okay, so if I calculate here, I'm going to get a value of negative 27.471 meters per second. Okay, so kind of like the previous case, all right, that vertical velocity is negative. We're on our way down, okay, but this is much faster now. And so if I was going to make this picture, okay, well, there's my Vx. Well, now my Vy is a lot bigger. See, it's got that magnitude of 27.4 or whatever, whereas the Vx was the 16.851. Okay, so we're still going down and to the right. Okay, but much more downward now. All right, if I want to calculate that speed, just like I did before, I'm going to apply a Pythagorean theorem. Vx squared plus Vy squared square rooted. So I get that 16.851 meters per second squared, plus that vertical, so that's that negative 27.471 meters per second squared. Let's move that over so that a little too cluttered. Okay, and if I throw that in my calculator, I'm going to get 32.228 meters per second. Okay, and again, this is like a diagonal speed, so there's no positive, there's no negative. We only got positive and negatives along our coordinate axis or our xy axes. All right, and then again, let's calculate that angle. So same approach as before. I'm going to inverse tan the vertical component over the horizontal. All right, so what do we got here? So I'm just going to look, again, I'm just looking at the magnitudes because I can see that my angle is somewhere between 0 and 90 degrees. So I'm just looking for the size of that angle. kind of what we do in physics. All our angles are complementary because they're so much nicer. All right, and then let's see. So what did I get? I get 58.475 degrees. Okay, so again, here's my speed. There's my direction, and I forgot to write that this is below positive x-axis, but again, I can see it right on the picture, so even if I didn't write that, okay, it's on my diagram, so that'll work. Okay, so I just took those initial conditions. So there's the 28 meters per second and 53 degrees, and I have kind of a side-by-side comparison, just so you can see what stays the same and what's the difference. Just when we change that one little number, okay, just that little dy, okay, so the components stay the same. We got the same acceleration of gravity. But once you change that vertical displacement, okay, well, that starts changing everything else. Okay, how long it's in the air, its horizontal displacement, how fast it's going. Okay, and the template stops with the components. We took it a step further and resolved the vector into its magnitude and direction. That changes too. If you look at kind of what we did here, okay, we had to solve for the time in each case. We used that to get the range. We used that to get the final velocity in the vertical direction. Notice here, I just wanted to point out really quick, okay, our timeless equation, I didn't choose to use it here because, well, even though I knew that the projectile was on the way down, I wanted to show you, okay, that by using that time, so in other words, like I went into this as opposed to using this, just so you could see that that velocity comes out negative. Remember, when we use the timeless equation, it only gives us the magnitude of the speed part of the velocity, doesn't give us the direction. So when in doubt, use VF equals VI plus AT, and that'll give you the direction too. Okay, so there's the last little look at the side-by-side comparison. And that's all I got, guys. Good luck going working these out. They take a little bit of practice, but you can do it. If you have any questions, just see me in class. I'll see you next time.